get on camera. Everybody had a chance to at least read the lab? At least read the introduction. We'll look at the pre-lab questions first, because they involve some basic concepts of calorimetry, plus we'll do some calculations with the pre-lab, and that'll kind of warm things up. Let's see, we've got what, about an hour left in the class. All right, so let's look at number 1, pre-lab. Pre-lab number 1. 1 mole of acid and 1 mole of base. Actually, this one refers to the method itself. One of the exercises in here is we're going to mix an acid with a base, and it's going to generate some heat, and we're going to measure that heat and compare that heat based upon, remember, we haven't talked about acid bases yet, have we? All acid base reactions are some type of acid plus a base yields that's a salt. Right, this cation with that anion, and then the hydroxyl and the hydrogen get together and they make water. Okay, that's typical acid-base reaction. So in solution, right, these are all aqueous solution. In solution, you've got these floating around and these floating around. So they're still floating around over here because this is still in solution. So you can remove those as spectators. Right, they're the same on both sides. So the real business of the reaction going on is between this one and that one. So this is the reaction. This is the net reaction for acid bases. Is the hydrogen ion plus the hydroxyl yields water. Okay, that's what this first problem is talking about. And once you decide how much heat is being produced in that reaction, you can prorate it to the amount of water that's being produced as a consequence of whatever the reaction is. In our case, we're going to have sulfuric acid plus sodium hydroxide. What's that going to make? Sodium sulfate. I need 2 of these. And water. Okay. So let me see. I need to balance that. 2 hydrogens, 1 sulfate. We need 2 sodiums. Now we've got 2 waters. There we go. That's balanced. That's the reaction that we're going to be using for one of the exercises in this lab, is the neutralization of an acid with a base. And it produces heat. So you're going to have heat out here, and we're going to measure that as a change in temperature. Okay. And we're going to be able to determine how much heat in terms of joules per mole of water. That's where we're headed for that one. So you need to know how much of this you put in and how much of that you put in, and do the stoichiometry, so you know how many moles of water are produced. Right? Okay. Once you know how many moles of water are produced and how much heat is produced, you get this relationship here. You get this quotient. Much heat divided by moles of water, and there's your value. And then at the back of the, let's see, of your copy, there's a table back here, right here. And this tells you what the expected value for that is. The one we'd be looking for is the one on the bottom. Right? H plus OH minus yields H2O. That's minus 57.9 kilojoules per mole. And that's per mole of water. So you compare the value you get to this value. And notice It's a negative sign. And that means what? Exothermic. Everything is in relation to the system. So the system generates heat and it leaves the system. So that's why it's got a negative sign. All right, so I said all that so that we could make sense of this first question. The first question in the PreLab is 1 mole of acid and 1 mole of base react to form 1 mole of water. So 1 mole of this reacts with 1 mole of that to yield 1 mole of that. Right? That's stoichiometric. 1 to 1 to 1. Okay. Now the question is, why do we use an excess of this one? Which for our experiment would be in excess of this. Why do we use an excess of sulfuric acid? And this would be our limiting. So we're going to make sure that all of this is used up. And we're going to have a little bit of that left over. Why do we do that? Got any ideas? Do you think that you can measure out exactly 1 mole of this and exactly 1 mole of error? You're trying to be sure that the reaction goes to completion for that mole of hydroxide. We could do the same thing if we had this in excess and that 1 mole. It'd work just as well. You'd be sure that you used up that mole or however much you put in there. So we have this in excess in our case, so that all of this is used up. And even if there is a little bit of error in there, we know the reaction goes to completion. Right? That's why you use an excess of sulfuric acid, just to be sure that the reaction goes all the way to completion. Otherwise, if you think you got a mole there and a mole there, you don't know which one is which one is really excess and which one's really limiting. We're guaranteeing that this one is excess and that one's limiting. Okay, that was one. How about number 2? Let's see, what does it say? You are an engineer. Well, maybe I wish I was for the money. Engineers make more than teachers do. To choose, you're an engineer assigned to choose a material that will protect the spaceship from destructive heat when it re-enters the atmosphere. And you got to choose aluminum or iron. Well, that right there makes this whole problem improbable. Right? Nobody's going to use either one of those as a heat shield. Well, maybe the aluminum. Because you got to get it into space first, right? And every ounce costs a lot of money. But that aside, if our choices are aluminum and iron, considering only the heat capacity. So they understand the problem too, right? We're not talking about mass. We're talking about heat capacity. The molar heat capacity of aluminum and iron are respectively. So the molar heat capacity of aluminum is 2435. And that's joules per degree C mole. And this is not specific heat capacity, this is molar heat capacity. If it was specific, there'd be grams there. And then for iron, was it? The molar heat capacity for iron is 25.10 joules per degree C mole. Okay, so which one would be more effective as a heat shield? Well, let's look at, say you have a certain amount of heat that has to be absorbed. It's the same for either one for the spacecraft coming in. So what is that based on? Well, it's based on the heat capacity, and then it's based on the mass, and it's based on change in temperature. So this will be different for each of the calculations. I assume we're using the same number of moles of each one, so we're holding this one constant, right? Isn't that what they said? They said considering only the heat capacity. So that means they're making this one constant, and the change in temperature will be the one that varies, because we've got a certain amount of heat that's constant and the mass is constant. So we're letting these vary. So how do they vary? Remember, a product, Boyle's law. A product of variables equals a constant. Those are inversely proportional, right? That's a constant. These two have to go, one goes up, the other goes down, right? So these two terms here and here are inversely proportional. That means the if this one goes up, the change in temperature goes down, and that's what we want. We want the temperature to be, change in temperature to be lower. So we want this one to go up. So that means based on heat capacity only, iron's the best choice. Now you can rationalize it without using a formula. And you can say, all right, what does heat capacity mean? It means how much heat can you absorb and still only change the degree, the temperature by 1 degree. Right. So this one can absorb more heat to change only 1 degree than this one can. Okay. I mean, it's a slight difference, but there it is. Any problems, questions with that? Make sense? Okay. All right, let's see, number 3. Number 3. The enthalpy of solution of sodium hydroxide. What does that mean? Enthalpy of solution. When we take sodium hydroxide, solid, and we put it in water, and that makes an aqueous solution of sodium hydroxide. This is exothermic. It's going to generate a lot of heat, and I mean massive. If you try to do that with a little bit of water and a lot of sodium hydroxide in a plastic vessel, then it'll melt out the bottom. Okay, so that's why we always do it in glass. So there's amount of heat that's generated from that. And this can also be rated by mass or moles of sodium hydroxide. Okay, and it's given it to us here as minus 44.5 kilojoules per mole. So the enthalpy of solution is equals minus 40, what? 44.5. Yeah, 44.5 kilojoules per mole, and that's per mole of sodium hydroxide. Okay. So for every mole that goes into solution, in fact, no matter how much water it is, going into solution is still going to generate this much heat per mole of sodium hydroxide. So if you have a small amount of water, same amount of heat will be generated, which means the temperature is going to be higher. So usually there's a rule of thumb. You've ever heard the do as you ought to add acid to water? Okay, that means when you dilute a strong acid, put a little bit of acid in water and build it up from there, because that large capacity, large volume of water will absorb more heat, and you won't get instantaneous flash evaporation and blowing on your face. If you did it the other way and you have acid, you know how much acid you want, and you're going to add water to it. And you add water, a little bit of water, and it goes, a little bit of water, right? So you go the other way, and the same thing happens with bases. Right? Bases and acids going into solution generate a lot of heat. So back to the problem. If 10 grams of sodium hydroxide, so we got 10 grams here. And let's see, 10 grams sodium hydroxide dissolved in 75 milliliters of water. 75 milliliters of water. Okay. And the water starts, the initial temperature of the water is 21.1 degrees C. What would be the maximum temperature attained? And the heat capacity of the calorimeter. So we haven't talked about that yet. The calorimeter, that big C, remember that formula we had, Q equals, this was Professor Dave was talking and he had two formulas up there. Yeah, C delta T. And he also had one up here. It was the one we're familiar with, which is heat capacity, mass, or moles times temperature. So this C is the heat capacity of the calorimeter. And by the way, once you set up your calorimeter, and we're going to determine what the heat capacity of your calorimeter is, that's the first step. Then when you reconstruct that calorimeter to do the experiments, you have to use all the same parts you did when you made that, because the variables in here are built in. So if you change anything in your calorimeter, it'll give you a different C. So once you determine the calorimeter constant for your calorimeter, don't change anything. Don't use a different thermometer. Don't use different cups. Don't use a different lid. Right? All the same stuff. Okay, so it tells us the calorimeter constant here is, where was it? 1 times 10 to the 1 joules per degree C. What's 10 joules? 10 joules per degree C. And notice that value doesn't have any mass units in it. Well, we erased them all. Instead of moles, it'd be mass. Okay, so that's everything that we're given. And the question is, what's the final temperature? What's the final temperature? Okay. Okay. So here's the way you set that up. Remember, your calorimeter is an isolated system. That means everything in Vegas stays in Vegas. Everything in that calorimeter stays the same. Anything that happens in there adds up to 0. All heat changes have to be 0 because it's isolated. So that's why we say, I'm still on, kind of getting close to the edge there. Let me, I guess I can squeeze it in here. 0 equals, what are the heat changes that are going to take place? Right. 1 is the heat of the reaction. And that's attributed to the heat of solution here. Okay. And then we think this is, even though everything's mixed together, it's convenient to think of what's happening in there in compartments. So the reaction is one compartment, the water and its temperature change and heat capacity are another compartment. And then the third compartment is the Q of the calorimeter. Okay. That's typically what you'll be looking at, particularly with the procedures that you're going to have in the lab. You'll have a reaction heat, you'll have a water heat, you'll have a calorimeter heat. Okay, so in this case, how would we write the Q for the reaction? Well, we know how many grams we're putting in solution, and we know the heat of solution for that one, but that's in moles, and that's in grams. So in order to use this, we need an expression that gives us S moles delta T. So this needs to be converted to moles. in grams. So we need a molar mass here for sodium hydroxide. Let's see, sodium is what, 23, I think. This room doesn't have a periodic table. So let's see. Wait a minute, I've got the key. Just look here. 40, total of 40. So oxygen 16, hydrogen's 1.01, sodium's 23. So we're going to use 40. There. And that's 10 divided by 40 is 0.25, isn't it? 0.253 moles of sodium hydroxide. Okay. Right. So that would go in here. And then specific heat. Oh, there it is. No, that's heated solution. Kilojoules per mole. Oh, okay. I'm sorry, I'm misleading you guys. This heat term is entire. We're going to calculate that heat term from the number of moles of sodium hydroxide and its heated solution. So once we got these number of moles, then all we need to do is multiply minus 44.5 kilojoules per mole. And that'll give us the heat of the reaction. Let's see if I've got it in here. Yep. It's minus 11.1 kilojoules, right? But these other terms are in, where is it? 10, are in joules. So we need to convert this to joules. Right, so how do you go from kilojoules to joules? Simplest way is to say, what does that mean? That's 10 to the 3, isn't it? Right. So this would be a minus 11.1 times 10 to the 3, or minus 1.11 times 10 to the 4th joules. So that's the term that goes here. Pretty sure. Yep, that's the term that goes here. Minus 1.11 times 10 to the 4th joules. Okay. Now what's the Q of water? Well, the Q of water, we're going to use this one right here. 75 milliliters of water is 75 grams. The density of water we're going to assume is one gram per milliliter. Okay. So in this term, we need, what's the specific heat of water? I think it's 4.184. Check this out. Yeah, joules per gram degree C. And that is times the mass, which is 75 grams. And then times delta T. Delta T is final minus initial. Right? We don't know what final is, but we do know what initial is, 21.1. Okay, that's the second term. The third term is the calorimeter. So the calorimeter is going to experience the same temperature change because we put the water in the calorimeter first, and that's when the temperature was measured. So they're both at the same temperature, the calorimeter and the water. So in this one, we don't have this term right here is combined in that one. Notice that grams cancel, leave you with joules per degree C, joules per degree C. So this term, I have to put it down here, is going to be just the C value, 10 joules per degree C. And that's times TF minus 21.1 degrees C. There. There we go. So that's the whole string there. And you'll notice we've only got one unknown right here. So we can solve this equation for that one unknown. That's what we have to do next. Okay. So I'm going to erase some of this. Not with that one, this one. So that we can do some ciphering. Okay. So let's do it this way. 0 equals minus 1.11 times 10 to the 4th. And then expand this one. So this is 4.184 times 75. Which is 3. Let's see. I'm going to keep 3.138 times 10 squared. 3.138 times 10 squared here. And that's times TF. And then minus that value times 21.1. Right? We're distributing this one through the entire, we're taking this times that and this times that. So I need 21.1 times that value also. 6.621 times 10 to the 3rd. Here we go. So that came from right here. This expression resolved into these two numbers, that one and that one. And then this one is 10 times TF. Okay. Minus 10 times 21.1, which is 211. Okay. So now what we need to do is let's see, now this is a plus. Sorry, that's a plus. All of these are pluses and minuses. So we can add all the numbers together and then we can combine the ones with the unknown. And let's do that next. So minus 1.11 exponent 4, change that sign. Nope, wrong sign. 1.11, change the sign, then exponent 4. Okay. Then we're going to add to this one, which is another minus 6.62 sine exponent 3. Okay. So this is that one plus this one is a minus 1.772 times 10 to the 4th, but we've got another one over here, that minus 211. Okay, so the numbers come together as minus 1.793 times 10 to the 4th. And then the ones with the unknowns, we just take this one and add it to that one. 3.318. Yep. Exponent 2. And then add 10 to it. 3.418. 3.418 times 10 to 2. Just checking myself. Let me do that again. This one's 313.8, isn't it? Plus 10. Yeah, that didn't look right to me. 3.238. 3.238 times 10 squared. And that's times TF. So we need to put this one on that side, right? Make it positive on this side, and then divide it by this one. So TF should be equal to 1.79 times 10 to the fourth, 793, divided by 3.238 times 10 squared. And let's see, do I have these in here yet? Yeah, but they're not together. 1.793 exponent 4. Then switch them and then divide. So this one is 55.4 degrees C. That should be the maximum temperature we can arrive. Okay, that was a lot of work just to get that one number, I know. But it is methodical, right? If you follow this format where everything is equal to 0 and you line up what are my terms, what are the compartments that are accumulating or releasing heat, and then go to each one of those and say, how do I get that answer? That was number 3. Okay, that's all the pre-lab questions. Now we can talk about the method. Okay. Let's see. There we go. Okay, so the first thing we're going to do is determine the calorimeter constant. Okay, the calorimeter is going to be, let's see, draw these. It's going to be a cup within a cup. Styrofoam, 2 styrofoam cups, one inside the other. That effectively isolates your system from the outside. The only real problem, this is not a problem for isolation. The problem that arises is in the lid and the thermometer. Okay. And that's the whole thing. Remember, I said I took the stirrer out of it because it kept corroding. It was just more trouble than it was worth. And we can use the thermometer if we're careful and stir it around. Okay, so everything that's going to happen will happen inside there. All right, what we need to do is find out what's the heat capacity for that. How many joules per degree will it absorb or release? All right, so the way you do that is you just use water. Right? We're going to have 2 samples of water. I think each one is 75 milliliters each. We're going to use distilled water. So you're going to have, you're going to put 75 milliliters of water in here. 75 milliliters of room temperature water. And let it equilibrate with everything that's in there before you measure its temperature. And then you're going to have some boiling water over here on a hot plate. And like that. And this is going to be, it won't be 100 degrees. You're going to have to measure it. So you'll take out of this, you go into a graduated cylinder, right, with its markings, and you want 75 milliliters here of boiling water. Okay. Now, when do you measure the temperature? In here? No, because once you put it in here, it's going to, some of the heat's going to go into that glass. Right, so you don't want to measure the temperature until right before you put them together. And then you'll have a different thermometer. You'll need 2 thermometers. You put a thermometer in here. Right? Put a thermometer in here. Measure the temperature. And immediately after measuring the temperature, you dump them together. And of course, be sure and record the values. So you'll have a temperature here, initial temperature there for that one, and you'll have an initial temperature here for that one. Right? This will be initial cold and initial hot. Okay. What's the final temperature? Once you mix them together, they're both going to have the same final temperature. Okay. Let's see. Okay. So the formula, we've got these compartments. One compartment is for the hot water. One compartment is for the cold water, and the other compartment is for the calorimeter. Okay. So let's see. Let's set up our 0 equals the heat for the cold water, right? Plus the heat for the hot water. Whatever happens in the cold, whatever happens in the hot, plus the Q for the calorimeter. All right. So now we can expand these. For the cold water, we're going to have a specific heat for water. We know that value. We're going to have the mass for the water. We know that value, 75 grams. And the temperature change is final, will be the same for everything, but for the cold, it's going to be Ti cold. Okay. We do the same thing for the hot. We have the same value here for that water. We have the same mass, have the same final temperature. We have a different initial temperature. Hot. And then the calculation for the calorimeter is simply C times delta T. Right? C is unknown. That's what we're going after. And here we have final temperature minus what? The initial temperature is the same as the cold, because we put the cold water in the calorimeter first. So this one is exactly the same for this one. Okay. I'm sliding off the edge of my screen there. All right. So we know what this is, right? 4.184. We know what this is, 75 grams. Whatever the final temperature is, whatever the initial temperature of the cold is, these two values are the same as those. And you'll get these values, you measure these values, you'll measure these values, which are the same as those, and then solve for that one. Okay. It could be almost anything. Right. That previous problem, they were usually 10 joules per degree C. If you don't know what the value is, then you can use 10 joules, but it's probably not going to be that. It's probably going to be larger. Okay, I can't finish it any further because we don't have values for these temperatures. Well, I do have an example. In your method, don't I have an example at the bottom of the page? Determine a calorimeter constant. Yeah, there's an example down there. Well, that one doesn't help much either because there are no values, right? So once you determine that value for C, that's the one you're going to use in every other calculation where you're accounting for the heat capacity of the calorimeter in your calculations. All right. So then we have three parts. After that, we have 3 parts in the experiment. There we go. We don't do that. So part 1 I think, is the acid-base neutralization. Yeah, enthalpy of neutralization. The reaction that's taking place. It's always good to have a when you've got a chemical reaction going on, a balanced equation always helps. So in this case, we're putting sulfuric acid together, and I think I wrote this one up there already. Sulfuric acid in an aqueous solution plus sodium hydroxide in aqueous solution yields sodium sulfate in aqueous solution plus water, pure liquid. Let's see, I got to balance this thing. 2 of these and 2 of these. There we go. Okay, so we're using 0.5 molar sulfuric acid. 0.5 molar. We're using 60 milliliters. Right. And we're using 1 molar sodium hydroxide, 50 milliliters. Now, why is this one twice the concentration of that one? Because of this ratio here. It takes 2 of these for every 1 of those. So instead of using the same concentration and having to jack the volume up so high, we just make this one double the concentration. And then if we could measure exactly the right number of milliliters, this will be 50 and that'd be 50. Right? But we can't. Right? There's always error. So this one's the excess. That's why it's 60 milliliters. Okay. And from this, you can calculate how many moles of water will be produced. Right? How many moles of sodium hydroxide are going into that solution? Because this is the limiting reactant. Right? We have to go with this one to calculate the moles of water. Right? Have I shown you the millimole thing yet? Okay. When you multiply molarity times milliliters, you get millimoles, not moles. All right, so 50 times 1 is 50. Let's see. Yeah, we only got 2 figures. 50 millimoles. That just means 1,000th of a mole. Okay. So the ratio here is 2 sodium hydroxides for every 2 waters. That means this is 50. This is also 50 millimoles of water. Okay. Now, when you do your calculations, you need to use moles. But now that we know how many millimoles it is, what does milli mean? Milli means 10 to the minus 3, doesn't it? Okay, so 50 times 10 to the minus 3 moles. I just converted that milli into a number. And that would be 5.0 times 10 to the minus 2 moles of water. Okay. So whatever heat of the reaction you come up with, you'll divide it by this and compare it to that value that I showed you at the end of in that table. Okay, so what would the equation look like? Right? It still starts off with 0. Right? You're going to have the heat of the reaction. Correct? And then you're going to have the heat of the water. Okay, we have to assume, right? We have to assume that we're not going to create all that much water. Right? All the water that we need to account for is just 60 and 50, 110 grams. Right? If we were really anal about this, we would calculate how many milliliters that was and add it to that. But this is a student lab, so we're just going to go with 110 grams of water. Okay, so we got 110 grams of water. And what else? We got the Q of the calorimeter. Okay. So now we can expand them. What's the Q of the reaction? Well, that's the unknown. Right? We can leave it alone. The heat of the reaction will be so many joules. Once we solve it, that's our unknown. The Q of the water is going to be 4.184 for the specific heat of the water. And then the mass of the water is 110 grams, right? And then the change in temperature will be whatever final minus initial. And then the calorimeter is going to be the calorimeter constant times the same change in temperature. Okay. Now, there's one trick that you have to be careful about. What's the initial temperature? We know the final temperature because once you mix it together, you measure that. What's the initial temperature? If we're putting all the water together here, that means that the initial temperature of that and the initial temperature of that have to be exactly the same before you put them together. Otherwise, you have to split this term right here, split it into two for different initial temperatures. It can be done, but it's a pain. All right. So that's one thing you need to watch out for. When you're setting up and getting ready to go for this experiment, these two temperatures need to be the same. Okay. All right. So once you find out what this Q of reaction is, and you know how many moles, you divide this one, joules, by that one, moles, and you get a value. That's the enthalpy of the reaction. And it'd be close. It may not be exactly that. But then you know how to calculate percent error. So you just take your number and that number and calculate percent error. And that's what you report. Your value plus the percent error. Okay. So that was the neutralization reaction. Part one. We're good to go to the next one. Okay. There should be a pattern developing here. Even though we're using different reactions. Part 2 and part 3 are both heats of solution. Right. Part 2, we're mixing sodium carbonate with water. Sodium carbonate. Now, this is not going to be, we could write sort of an overall reaction. Sodium carbonate. Solid, and then we're going to put it in water. And it's going to make a solution of sodium carbonate. Okay. So we're going to start off with, let's see, 10 grams of sodium carbonate. Now this is nominally 10 grams. What you're going to do is you're going to weigh it on analytical balance and get out to 4 decimal places. Right. So that's what your target is. Doesn't have to be exactly that. It can be under or over by a little bit. It's okay. As long as you have the exact number. Okay. Once you have the exact number, then you can convert it to moles. Because this table at the back, let's see, here it is. Sodium carbonate, second one down, is kilojoules per mole of sodium carbonate. So you need to convert this to moles. You need a value here for the molar mass of sodium carbonate. I don't know if I have it or not. Sodium carbonate. Oh, there it is. 106 grams per mole. Yep, 106 grams per mole. Or you can look on the bottle when you weigh it out. The formula weight will be there on the bottle. Or you can calculate it either way. And this will give you the moles of sodium carbonate. Okay. Now you hang on to that, because the next thing you're going to do is set up the calorimeter with 75 milliliters of water. So the mass of water equals 75 grams. Okay. All right, so after you record the temperatures, you record before temperature and after temperature. What's it going to look like? You're going to have another cue of the reaction. Right? Then you're going to have a heat change for the water, and you're going to have a heat change for the calorimeter, just like before. Right? This is going to be intact. That won't change. And this one's going to be your 4.184 times 75 grams. And here's another case. We have to assume that the heat capacity of the sodium carbonate has little or no impact on this. And it's probably true, because water has very high heat capacity. I mean, that's really huge. And most solids. All right, what was that example we did in lab? It was like an iron ball, not in lab, in lecture. And it was about a tenth of that. It's like 0.4. We use that as our example. And then times final temperature minus initial temperature. Okay. And then the calorimeter will be whatever your calorimeter constant is by the same thing. Same temperature change. And then this will be a factor out here, Q reaction. This will be your unknown. So you have values for all these, 0 on the other side, solve for that one. And then when you get this value, let's see, sodium carbonate, I'll give you a hint. It's an exothermic reaction. So it's going to be a negative number. And you can look in that table and should be a negative value. Let me see. Use government gobbledygook. It says, I may have misspoken. Yeah, it's a minus. So you just take the moles and divide that into the value you get here, and then compare it to that number. Okay. And number 3 is very similar. Very similar. You'll have this compound, sodium hydrogen carbonate, or as it used to be called, sodium bicarbonate. Right? There was a time when if you had a sour stomach, that was the thing. You just dissolve some of that in water and down it, and it would neutralize the acid in your stomach. Or if you're like my dad, you get up in the middle of the night and grab a handful of crackers and crumble them up in milk. Down that. No, not just milk, buttermilk. Anybody like buttermilk? That's pretty good. The acid in buttermilk is lactic acid. And lactic acid is a weak acid. We haven't studied that yet, I don't think. No, get that second semester, equilibrium. And what it will do is it will tone down the hydrochloric acid, because it's a weak acid. It buffers the system, right? That's the short version. The long version comes next semester. Okay, so 3, we'll do this, and we're going to use a different mass for the bicarbonate. It's about 7, is it? 7 grams?
7.0.
7.0, yeah. Close to 7.0, right? It's, again, you don't have to get exactly that. And then the molar mass is sodium, that's sodium carbonate, sodium bicarbonate. Wait a minute. Sodium carbonate. Oh, I found a mistake in this one. Look on step 5B.
Calculate the moles of sodium carbonate required to liberate 62.7 kilojoules. That should be sodium hydrogen carbonate. Shouldn't it? If you look at the 5 above, now design a cold pack using sodium hydrogen carbonate. Right? And 5B says calculate the moles of sodium carbonate. That's an error. It should be sodium hydrogen carbonate. You see that? Or did I correct it on your copy?
I don't even see 5B.
Yeah.
You know?
Yeah, 4's last.
Whoa, wait a minute.
For both of them, that's good.
Let me show you. Okay. I had more boo-boos than I thought I had. There's 5.
Okay.
I think.
Oh, some of the questions?
Yeah, questions.
Oh,
Yeah, not procedures.
yes.
I'm sorry, lab questions.
Yeah, we have 5. I don't see a B though.
Okay. No, it doesn't have. So now design a cold pack using sodium bicarbonate. Okay, you're good. All right. This is a key. I must have added these statements in here. Right, so all I have to do is correct my copy and yours is good. All right. Okay, back to the problem. So we need to know what's the molar mass of sodium hydrogen carbonate. And that I believe is 84 grams. Be sure when you're in the lab to check these values off the bottom, just to be sure I'm not telling you wrong. That will give you the number of moles of sodium hydrogen carbonate. Notice we only have one sodium in this one, because hydrogen carbonate is a polyatomic ion with a 1- charge. So we only need one sodium. That's why this value is less. And then you'll get the moles there. And this will set up almost exactly the same way, except you'll have different temperatures. And you'll come out with a positive. See, when you calculate the delta H for this one, it will be positive because it should get cold. The temperature should drop. Okay. So the final temperature is going to be less than the initial temperature. And then the way the algebra works out, that minus gets put on this side makes it positive. So your solution is positive. Whereas with the sodium carbonate, the final temperature is higher, which gives you a positive on this side. When you switch it to the other side to solve for that one, it becomes negative. Okay, and then that value is compared here also. Sodium bicarbonate is 17.15 is accepted value. I don't know why we threw the sodium chloride in there. Probably because it was built into the table. But those bottom 3 are the only ones you're going to need to work this out. Okay. Now we do have some post-lab questions.
So this one's gonna be endothermic.
Yes, it's going to be a cold pack. So I'm not saying that sodium carbonate, sodium bicarbonate are the materials used in hospital cold packs and hot packs, but the same type of reaction is occurring. So the hot pack is filled with something that will release energy when it's dissolved. Got a little capsule in there and you break it and shake your bag up. And the other one will go the other direction. It'll make it cold. In fact, the ones that I've tried in the hospital, they get really hot and really cold. It's amazing. Okay, let's see. Laboratory questions. 1, 2, and 3 are going to be unique for each group because they're based upon the results that you get. So when you have lab questions like that, where they're referencing using data that you collected in the lab and you're working out those problems somewhere else in your report, when you get to these questions, you can say, question number 1, refer to and point me in that direction. And 2, point me to that one. 3, point me to that one. Okay. When we get to 4 and 5, these are actually worked out. They'll be the same for everybody. Because you're given the data here to do the calculations. I don't want to work the whole thing out for you, but I want to give you some direction. Let's see. Number 4 is, I believe, the hot pack. Yeah, sodium carbonate dissolved in a pack. Calculate the heat required to raise the water temperature 30 degrees. No, that's my notes, excuse me. I'm looking for the question. Design your own hot pack. If the desired temperature of the hot pack is 50 degrees Celsius, and you're starting at 20 degrees. So there's your final temperature, and your initial temperature is 20, your final temperature is 50. That gives you that part of the equation. I'm trying to think. Okay. The end product here is if the water in your cold pack or hot pack, and I believe they're both 500 milliliters or 500 grams each, then what you need to do is calculate how much mass of each one of those compounds needs to be in that pack to give you that temperature change. Okay, so let me see if I can give you some queries and get you close to it anyway. First thing to do is organize your thoughts. These are word problems, essentially. So you need to extract this information and throw it on the board or on your paper. So number 4, what are we given? Final temperature equals 50 degrees. Yeah, 50 degrees C. Initial temperature, and this is for the hot pack. Initial temperature is 20 degrees. Okay. Yes, the mass of the water will be 500, should be a point there, grams, because it's milliliters, it'd be grams. And then the compound that's going in the solution is sodium carbonate with a molar mass of 106 grams per mole. Okay, other things that you'll need, specific heat of water. Right, that's 4.184 joules per gram degree C. And that should get it for you. Now we can break this into 2 pieces. One is, how much heat are we talking about here? Right. How much heat is this going to generate? If we just look at this simple expression, that'll give us the amount of heat for this reaction. That Q, right? 4.184, and then the mass is 500. And then the temperature change is what? Final is 50 minus initial, which is 20. Okay, that'll give you the amount of heat that's required in this process. Now, it won't have the right sign on it, right? Because this is going to be a positive number. But that'll be the amount of heat liberated in this process. Or if it'll make you feel better, you can just stick a negative there because we know it's going to be exothermic. And then calculate that value. Whatever that value is, you got a Q for the reaction. Okay. Now, Oh, we're also given, no, we're not given. You have to look it up. The heat of solution for sodium carbonate is in that table in the back, minus 23.3 kilojoules per mole. So the heat of solution for this one is minus 23.3 kilojoules per mole. Or, let's see, should we convert it? No, it's not necessary. I think. We can either convert this one to joules or convert this one to kilojoules. But they need to be the same unit of measure. And if this is the amount of heat, this Q of reaction is the amount of heat in joules, or let's say we convert it to kilojoules. Right? So whatever the value is, you just move the decimal to the left 3 places, and that's kilojoules. Oh, excuse me. Yeah. That's right. That's right. Took me a second. This Q of the reaction is actually just the joules or kilojoules. So, and this is going to give us, it's already kilojoules. So if we say minus so many kilojoules here. That's what we get from this reaction, this calculation. Now we want to convert our units to moles. So we need kilojoules on the bottom, moles on the top, right? So we put the moles up here, kilojoules down here, 23.3. This is a negative and that's a negative, so we come out with a positive number. Then you're going to end up with so many moles, Y moles of sodium carbonate. Okay. That tells you how many moles of sodium carbonate you need to make this temperature change in 500 milliliters of water. Okay, that value. You've got the moles of sodium carbonate, just convert it to grams. Use the molar mass. Okay. So what would that be? We have moles on the bottom, grams on the top. So it's what, 106. Right, 106 times that value will give you the mass of sodium carbonate that you need to make that happen in 500 milliliters of water. Okay. And you do a similar type of thing for sodium bicarbonate. You'll have different values. It wants you to do what? Go from 20 degrees down to 1 degree. So for 5, I'm out of time. So for 5, we're going from 20 initial down to 1. There. Same amount of water? I think so. Yeah, 500 mils. There's going to be a different compound here with a different value. What was it? 84, I think. Yeah, 84. So that's that one. And I don't think we need a negative here. Because we know this is going to be 1. Well, that'll give us a negative value. Yeah, we do need a negative. Sorry. Because we need a positive value. And that'll give you the kilojoules for that reaction. And then you need a different value here. Because this solution is, I think it's 17.15. This is positive 17.15 kilojoules. So this one is going to be positive 17.15 kilojoules per mole. And this is how many kilojoules will be produced in that reaction. That tells you how many moles of sodium bicarbonate, and then you multiply it by 84. And that gives you the mass of the sodium bicarbonate to do that cold pack. Okay. Almost handed that one to you on a silver platter.
Thank you.
Yeah.
Appreciate it.
Okay.
Don't erase that, Jet, please.
Okay. As convoluted as it seems, this is a logical process. Sometimes I like to imagine when I'm doing these calculations, imagine me in the lab and getting that data. It kind of keeps me grounded as I'm working the problems. That's it. So we'll come back on Tuesday. And let's see, what are we going to do in the morning?
So you were asking me that.
Is it a review?
Yeah.
Okay. So we're going to review those. Review from the work products. Chapter 6, just chapter 6.
Is that 0.84 grams of oil?
No, I'm sorry. 84. 84.0 actually.
Figure it out. Thank you.
So. Bring all your equipment. Bring your notebooks, we're ready to be looked at. Okay. And have fun.
Now, our last week's lab will be due Tuesday.
Yes.
Okay.
Yes,
Awesome.
the Boyle's Law.